We're going to talk about different types of variation in this section. First, we'll start with direct variation. So sometimes a variable can be directly proportional to another variable. So as one variable increases, the other variable increases, and as the one variable decreases, the other variable decreases. A simple example is a relationship in cost. If C is the cost and X is the number of items purchased, let's say the cost is $3 each. Then cost is directly proportional to the number of items. So cost would equal to some constant times X. So as X increases, the cost increases, and vice versa. Okay, so if Y is said to vary directly as X, it's also the same as saying Y is directly proportional to X, then their relationship is described by Y equal Kx, where K is some constant of variation. So let's take a look at that. Suppose the top speed of a race car in miles per hour varies directly on the size of the engine, in cubic centimeters. If a 450 cubic centimeter engine allows a top speed of 200 miles per hour, how fast will a car go with a 600 cubic centimeter engine? Well, let's let S equal speed, and let's let X be the engine size. So here we have the speed is directly proportional to the engine size. Well, we can find this constant by simply plugging in what we know. We know when S is 200, the engine size is 450. So we know that 200 must equal 450K. Just plugging it in here, 200 here for S, plug in 450 for X, and then just write the K to the right instead of the left. And then if you divide both sides by 450, you get K is equal to 200 over 450, which reduces to 4/9. So now you've got the model that describes the relationship between engine size and speed. So now if I want the speed of the car when the engine size is 600 cubic centimeters, I just plug 600 in for X and then grab my calculator, and I got roughly 267 miles per hour. So that's direct variation. Sometimes one variable can be inversely proportional to another variable. And this is we're going to talk about inverse variation. So as one variable increases, the other variable decreases. As one variable decreases, the other variable increases. A simple example is the relationship in a pitcher's velocity of a pitch and a batter's batting average in baseball. As the pitch velocity increases, the batter averages generally would decrease. The relationship might be something like this. X equals 50 over V, where V is the velocity and X is the batting average. If the velocity is 75, then if the velocity is 75, then X would equal 0.750. Actually, I had that wrong. 50 over 75 is actually 0.667. But if V increases to 100, then you get 50 over 100. So the batting average decreases from 0.667 to this right here, 0.500. So the batting average would decrease. So now, if Y varies inversely as X, or Y is inversely proportional to X, we say the relationship is described as Y equal K over X, where K is the constant of variation. So here's an example of that one. The number of revolutions per minute a gear can make is inversely proportional to the number of teeth on the gear. A gear with 100 teeth can make 200 revolutions per minute. How many teeth are required for 400 revolutions per minute? Well, we know that we'll use R for the RPMs, the speed, and T for the number of teeth. So we know revolutions is inversely proportional to teeth. So given 200 revolutions, we know that occurs when we have 100 teeth. So put 200 in for R, 100 in for T, and then solve this for K, and you get K equal 20,000. So basically, R is equal to 20,000 over T. And now let's find T for R equal 400. Well, let's put 400 in for R, and then you can actually just cross multiply this because really 400 can be thought of as 400 over 1. So you get 400 times T is 400T, and then 1 times 20,000 is just 20,000. And then if you divide 400 into 20,000, you get 50. So the number of teeth that correspond to 400 revolutions per minute would be 50. And so that's an example of inverse variation. There's another type of variation called combined variation or joint variation. So sometimes you might have direct and inverse variation combined in the same formula. So, suppose a variable z varies directly as x but varies inversely as y. So as x increases, z increases, but y decreases. But as y increases, z decreases. So, for example, when a principal is invested at an annual simple interest rate of 5% for a time period t, the principal is directly proportional to the interest earned, but it's inversely proportional to time. So basically, we could say principal is equal to 20 times I over t, and that's if you invested $20. Sorry, I should have said that. But if you invest $20, you might get something like this. So if y varies directly as x and inversely as z, the relationship would be like this. Y would equal k times x divided by z, where k is the constant of variation. Now, suppose the strength S of a beam varies directly as its width and inversely as its length. If a beam with a width of 4 inches and 72 inches will carry a beam with 4 inches and length of 72 inches will carry 100 pounds, how many pounds will a beam of 6 inches and length of 60 inches carry? Well, let's get our model. We know the variation. S varies directly with W but inversely with L. So we know that the strength would be 100 pounds if the width is 4 inches and the length is 72 inches. So we can plug those numbers in, plug in 100 for strength, 4 for width, 72 for length, and then I simplified that. I got k over 18 because 4 went into 72 18 times. And then if you cross multiply, you get 1800 equals k. So k is 1800. So the completed model would look like this. And now it says how many pounds will a beam with 6 inches, so put in 6 inches for the width and 60 inches for the length. So I'm going to put in 6 inches here for width, and then I'm going to put in 60 inches for the length. Now let's see what happens. Well, if you divide that out, 6 goes into 60 10 times, so you get 1800 over 10, which is 180 pounds. Now these first two problems, examples of variation, go ahead and read those on your own. Freeze the video if you need to and try to work them. And then I've got the answers there. But like I said, these two are fairly simple. The first one is an example of direct variation. And the second one also is an example of direct variation. But notice in the second one, it doesn't vary directly with t, but it varies directly with the cube of t. So notice when I wrote the formula here, I said y equals k times the cube of t, so kt cubed. And then I plugged in my information and solved for k, and then when I get back to the model is y equal that k, which is 8, t cubed. And so, it doesn't have to vary directly or inversely as the variable. It could vary inversely or directly as the square or the cube or even the square root of a variable. So you got to read the problems carefully to learn how to set it up. Okay, let's take a look at a more complicated one. When you use a spray can and press the valve, you decrease the pressure of the gas in the can. This decrease in pressure causes the volume of the gas in the can to increase. Because the gas needs more room than is provided in the can, it expands in spray form through the small hole near the valve. In general, if the temperature is constant, the pressure P of a gas in a container varies inversely as volume V. So basically we know that P varies inversely as V. So P is equal to K over, where's my cursor at? P is equal to K over volume. And now this tells me that the pressure of a gas sample in a container whose volume is 8 cubic inches is 12 pounds per square inch. Okay, so basically, I didn't state that properly, but volume is 8 cubic inches, it has 12 pounds per square inch. So basically, if the size is 8 cubic inches, that's the volume. So if the volume is 8, the pressure is 12. Okay, so let's put that information in here. Put 12 in for pressure. Let's put 8 in for volume. And then you can cross multiply and get K is 96. And so basically your completed model is pressure equals 96 divided by volume. And so now it says if the sample expands to a volume of 22 inches, what is the new pressure of the gas? Well, we can put 22 in here for volume and get 96 over 22. So now we get that the pressure per square inch is about 4.36 units. Okay, one more. The centrifugal force C of a body moving in a circle varies jointly with the radius of the path R and the body's mass M, and varies inversely with the square of the time. So really we're varying jointly with two variables. So notice here we're varying jointly with both R and M. So I have K times RM. And then I'm varying inversely with the square of time, so that's going to be over time squared. So that's what we've got there. Now, it's going to tell me that, it tells me here in this sentence here, a 6-gram body, so that tells me that the mass is 6, moving in a circle with a radius of 100 centimeters, so we know that R is 100. So notice down here I put in 100 for R and 6 for the mass. And it travels at a rate of 1 revolution in 2 seconds. So let's see, it has a centrifugal force of 6,000 dynes. So C would be the force, 6,000. And let's see, where was the revolution? The T was the time for it to make 1 revolution, so that was 2 seconds. So I put 2 in there, but I got to square it, right? So basically I get 600K over 4, which is 150K, and then divide by 150 into 600 to get K equal 40. So now I know K, so this is my completed model. And now it says find the force of an 18-gram body. So I'm going to put 18 in for the mass of, let's see, moving in a circle with radius 100. So the radius is still 100. And then we got 1 revolution in 3 seconds. So now the time would be 3 seconds. And so when you multiply all this together and then divide by 9, which is what 3 squared is, you're going to get 8,000 for the result. So 8,000 dynes. So these are kind of some neat little problems, and they're actually formulas that are used in business and science. So hopefully this helped you. This finishes the Chapter 6 lecture, and so I'll begin a lecture on the next chapter of topics for Chapter 7.